Welcome to my Introduction to Networking course, typically abbreviated ITN. This will be for the CCNA version 7 curriculum. Module 4, the physical layer. So in the physical layer, we're talking about the purpose, the characteristics, and we're looking at the three main types of physical cabling: copper, fiber optic, and wireless. Yes, I understand wireless is not tangible, but it is classified as one of the physical layers, so we're going to talk about it in this module. So, what's the purpose of the physical layer? Essentially, before any communication can occur, there has to be that physical connection between multiple devices. That has to be established. Again, wireless is also included in this. This connection could be, again, wired or wireless. And how we do that is through an interface card, oftentimes called a network interface card, or NIC. The NIC, if it's wired, will be a wired NIC. If it's wireless, it will be a wireless NIC. If it's cellular, it will be a cellular NIC, and so forth. These interface cards allow us to gain connection to whatever type of network we're trying to connect. Some devices may only have just one NIC with one port. Some devices may have multiple NICs, both wired, wireless, and other. Some devices, like a mobile phone or cell phone, may have a cell phone, a cellular NIC, a wireless NIC, and a Bluetooth NIC. They may have more than just two, they may have multiple. Again, not all physical connections offer the same level of performance. Wired versus wireless, which is going to be better? That's outside the scope of this lecture, but that's one of the big topics that will be discussed when you're in the networking realm. What is going to be a better option? So what's interesting is the physical layer actually takes the frame, the Ethernet frame, takes the packet and the segment and the user data, and actually takes that entire package and it puts it into bits. The bits are electrical signals, typically, that go on the wire. If we're talking fiber optic, it may be light pulses. But essentially, we're looking at taking the packages and making it go on whatever physical media we are selecting. This is the last step in the encapsulation process. Again, we take the entire package, we break it down into manageable chunks, and we send it on the wire. And this allows us to go from our device to the next device in the network. If it is local traffic, it's going to go to that, probably a switch. If it is internet-based traffic, it will be packaged to be sent to the switch, from the switch to a router, and from the router to the internet. Essentially, each device will receive the bits, and then it will take it and it will reconstitute a frame out of those bits and decide what to do with it. So, what are some of the characteristics? Well, first of all, we're talking layer 1, so that means we have to look at the different standards, things like IEEE standard, the IATF standard, the ITU standard, the ISO standards, and so forth. These are governing bodies that outline how physical media should be. If we're talking copper cable like UTP, an Ethernet cable, well, how do we know how the cable is made? How do we know about the connection that is made? Well, those are all IATF-based standards. If we're talking how the signal is put on the wire, IEEE lays out the standards for how the electrical signal is put on the copper-based wire. So these organizations actually outline how these connections should operate, how they should be made, how they should be terminated and tested. So major components of the physical layer addresses different functional areas. That's going to be the physical component, the cable itself, the signaling, and the encoding/decoding of that signal. So the physical components, again, are the hardware, the media, the connectors, the connections, anything that is used to transmit the data, and that's going to be wired NICs, wireless NICs, the connection of the cable itself, all of those things. So let's talk about encoding. Earlier we discussed binary. Here is why binary is so important, because our bits are actually all binary bits. So encoding basically takes and converts the stream of bits into a format that's recognized by other devices on the network. Here we have voltage over time. And as we look at the time as it goes on, what is represented as a 0 and what is represented as a 1? That is going to be the encoding. You'll notice that a high rise in the middle of anything represents a 1. In the middle of each option, if it's declining, represents 0. And again, this is just for example. Here, this is a high rise, though this is falling, so this is a 0. While this is still high, when it gets in the middle, it falls, so it's a 0. Here, it's a high rise, and in the middle, it's rising, it's a 1. Here, same thing. It's a high rise, and in the middle, it's going up, so it's a 1. Here, even though it's high in the middle, it's falling, so it represents a 0, and so forth. There's different methods for encoding. It all depends on what we're trying to process. So when we talk about signaling, we can talk about maybe the digital signal being a positive or negative voltage connection. Maybe we talk about the amplitude, the height of a signal, AM, amplitude modulation. Maybe we could talk about the frequency modulation. That's the frequency, that's the length of the signal over a given period of time. Here we're talking height. Here we're talking length. Here we're talking our phase. You'll notice that here the phase shifts. If we're talking fiber optic, it's going to be light pulses. So again, it just kind of depends on the type of media that we're using to represent those 1s and 0s. So let's talk, how do we measure this? We measure the actual transfer of bits in two ways. Bandwidth, and that is the maximum capacity that a medium can carry. Not the actual, but the maximum. And how we actually state bandwidth are in bits per second. Little b PS. Whether it be bits, kilobits, megabits, gigabits, terabits, and so forth. It is different than gigabyte, big B. If we're talking storage, we're talking big B. If we're talking actual communication, we're talking little b. The difference is there are 8 bits in 1 byte. So there's a different factor of 8 when we talk little b versus big B. When we talk specific bandwidth, we have to understand certain terminology. Latency, that's delay. That's typically the amount of time that it takes to send a signal, including that delay. Throughput is the other form of actual measurement of data flowing through a wire. Throughput is the actual measure of bits being transferred. And goodput is the measurement of usable data. So basically goodput is throughput minus the overhead. Overhead are going to be things like the frame headers, the packet headers, resending, if we're having to do acknowledgments, all of that is traffic overhead. That's not part of the data. Throughput is the actual transfer of data. So now that we have some basic understanding of how we measure, how we have basic characteristics of the different medias, let's talk about what those medias are. Again, there are three main types: copper, fiber, and wireless. So the first one we talk about is copper. Copper is the most common type of cabling. However, copper has attenuation. And attenuation basically is the signal degrades based off the length of the cable. The signal strength is the same whether it be an inch or less than 100 meters. It is typical that after 100 meters, the signal starts to degrade. Keep in mind, 100 meters is about 330-ish feet. So the longer the cable is past 100 meters, the more likely that attenuation may occur. Also, there are two heavy limiting factors for copper cabling. It is susceptible to noise. And there's two types of noise: electromagnetic interference, that's electrical noise, and radio frequency interference. And that's typically called radio waves. And if there is cables pushed too close together, the EMI could cause crosstalk. And crosstalk is where one cable electrical signals may jump to another cable. So how do we mitigate some of these? We follow the appropriate international standards. They outline length, they outline termination, they outline proper storage and installation, and how far you can bend the cable and how you bend the cable. All of those are outlined in standards that we should be following. If we're talking how do we prevent EMI or RFI, maybe we do shielding or we do a specific type of grounding to kind of help mitigate those, which we will talk about both of those when we talk about specific type of copper cable in the next slide. Some of the types of copper cables can mitigate crosstalk by twisting cables appropriately. So it just kind of depends on what type of cabling we're talking about, because copper cables are not just one type. We have three types of copper-based cables, and that is the traditional coax. That's somewhat that you'd be seeing on like your TV. Coax is still very common in broadband and satellite and some other forms of communication. That is still a type of physical connection when we talk our data networks. The other are twisted pair cables. And twisted pairs come in two flavors: unshielded and shielded. You will notice, first of all, that our unshielded, each one of these cables is actually twisted at different lengths. And then the green is slightly different. So the twists actually matter, and how close they're twisted together actually matter. That helps prevent crosstalk, the electrical signal jumping from one cable to another. Here with STP, you'll notice in the background some tinfoil. Well, that tinfoil actually allows us to wrap individual pairs to provide shielding for the cable. That helps prevent EMI and RFI. However, that shielding is expensive. So STP cable is typically more expensive. So the key characteristic is the outer jacket for UTP. It will be a plastic cable. It should have some type of core cable that will be, again, a plastic or fiber. And then the individual twists of each pairs. There should be 4 pairs, an orange pair, green, blue, and brown pairs accordingly. Each pair will have a solid and a striped. So solid being all orange, striped being orange and orange-white. And that makes up those pairs. We actually have to make a cable according to color patterns. And that color patterns are based off of these pairs. Shielded twisted pair, again, we have individual shields between each pair of cables. That shielding provides protection. The cable itself could also be wrapped up in another layer of protection. STP provides better protection, but it's more expensive. And because all of this extra layers, the cable is harder to move. So that means it's a little harder to install. The pro is it provides better protection for EMI and RFI. Again, we already talked about coax being like our traditional TV, our TV being that F-type connector, and our coax is a plastic outer jacket, a metal mesh, a white plastic protecting the core. The core is typically made out of copper. That core is actually what makes the connection. The nice thing is, what we do is we strip away, when making the cable, we strip away the plastic, the metal, and we take a little bit of that white core, or the white plastic, and we expose it so we see the core. We want the core, the copper portion, to actually go through the cable. So typically when you're looking at like a coax cable for your TV and you look at the cable and you see a little center copper portion, that is the core of the cable. And again, typically if we're talking TV coax, we're talking F connectors. That's that guy right there. Coax is very commonly used in internet for like broadband, like cable internet, and in wireless. Connecting the wireless antennas typically use coax. So let's go a little bit more in depth in UTP. UTP again is unshielded twisted pair. We've already talked. There are 4 pairs and they're all twisted slightly different to prevent for crosstalk. Again, the variation per foot per wire prevents different forms of crosstalk. Some of the standards are outlined by IATIA. It doesn't matter if it says TIA, IA, or IATIA, same organization. The standards talk about the length, the connectors, the termination, and the testing methods. Very common is we have different types of categories of UTP cables. We can have category or CAT 3, 4, 5, 5E, 6, 6E, 6A, 7, 8, 9, and so forth. Basically, the higher the category, the newer the cable. Newer cable standards allow for better transfer of data. For example, it's really common Cat5 and Cat5e for deployments. Well, Cat5e can go about a gig per second. Well, the problem is if we're trying to do 10 gig, well, Cat5e doesn't work anymore for 10 gig. Cat6 is becoming the new standard for our data installation. Cat6 allows for higher speeds of data, and Cat6 could also include forms of protection on individual pairs. It also is made out of better material, pure copper, and allows for higher frequency of data transfer, thus allowing for more bits per second. Hence why Cat6 is better than Cat5e. So let's talk about our connectors. 2 types of connectors. A RJ45 head. You'll notice that there are 8 pins, 4 pairs of pins, We do not need to strip individual pairs of wire. These are metal teeth. When we go to terminate the copper cable, our terminating tool is called a crimper, and it pushes these metal teeth into the plastic portion of the cable, thus allowing a connection to form. We have RJ45 sockets, also called RJ45 keystones, and these basically give us a female port. So how do we know if we're making the cable correctly? A properly terminated cable will look like this. The important part is this center part here. We have this plastic punch down actually punching down onto the cable. Thus, if we're pulling the cable, that provides a certain level of protection. Here, we don't have that protection, so if we pull on the cable, we're actually pulling on the plastic core portions and thus can be damaged. So now let's look at the RJ45 keystones a little more in depth. We'll notice that there are certain colors here on both sides. So how does that work? Well, the colors outline different standards. There are two major types of standards, IATIA 568A and IATIA 568B. Notice the striped colors, stripe, solid, stripe, solid, stripe, solid, stripe, solid. Also notice the order. When we're talking basic communication, we have to make sure that four pins are correct in the process. If 1, 2, 3, and 6 are created and they're matching and they're done, basic communication will flow. If we want a full functioning cable, we need to make sure all 8 pins are correct. But as long as 1, 2, 3, and 6 are connected, basic communication will occur. We're not talking fast, we're not talking 100 megabit, gig or 10 gig, but, basic 10 meg-ish connection is definitely doable with 1, 2, 3, and 6. So when we're making a cable, we choose either A or B. Well, see, that's the thing. A straight through copper cable is the same standard on both sides. So we can do A on both sides or we can do B on both sides. Well, the issue with a straight through is it will have to connect to unlike devices. A computer to a switch, for example, will use a straight through. A switch through a router will use a straight through. What happens when we need to connect a computer directly to another computer? A straight through doesn't work. We have to use a special cable called a crossover. Crossover is standard A on one side and standard B on the other. So crossovers are used with like devices. Computer to computer, switch to switch, router to router will all use crossover cables. One consideration is this auto MDIX, and that's a cable sensing technology that will flip the cable if it detects that it's using a straight through. Not all devices have it, so the best practice is to use the appropriate cable standard. If we're talking like devices, crossover. Everything else we use a straight through. Lastly, we have this third type of cable called a rollover. A rollover cable basically is a DB9, a serial port on one side, and a RJ45 connector on the other side. This is used to program equipment. So, if we're talking straight Ethernet cables, two main types, straight through and crossover. You need to know where to apply the cables when wiring up a network. crossover like devices. Straight through is everything else. So moving on, let's talk about fiber optic. Fiber optic is not as common as unshielded twisted pair. Fiber optic is using a light source to send data. While fiber optic is definitely more suitable in certain networking situations, it is a little more expensive. The light could be either a laser or LED, and the core portion of the fiber optic cable could be glass or plastic polymer. How fiber optic works is it will send a light using wavelength, and the cable itself will guide the light between one end and the other end. This actually allows for the minimal signal loss while sending light signals throughout the cable. So it's important to point out that fiber optic is a pair of cables, one for sending, one for receiving. Fiber optic comes in two other flavors, single mode and multi-mode. You'll notice that single mode will have typically a smaller core, and it will use a laser to shoot the wavelength through the cable. Single mode is made for longer distances, while multi-mode allows for multiple signals to be sent through different angles. It will use a much larger core, and it will use a LED instead of the laser. The LED allows for the transmission of light at different angles. And typically multi-mode does still go longer distance, but it doesn't go as long as single mode. Again, light over X amount of length will eventually degrade, but we're talking thousands of meters as opposed to feet. Fiber optic comes in a few different flavors, like fiber to home, fiber to the building, things of that nature. Well, we also have transatlantic or transoceanic connections. Those are fiber connections that go underneath the ocean to other continents. If we are talking large fiber connections between large cities, those are going to be long-haul networks. So connecting Vegas to LA, there's a long-haul cable that connects the two. Connecting Seattle to LA, again, long-haul cables. So common fiber connections are going to be a few different types of different connectors. We'll have a straight tip connector, we'll have a SC connector, we'll have an LC connector. That LC, you may only see one portion of it, but in reality, they come in two. They do not allow for single or half duplex. They only do duplex, one for sending, one for receiving. The nice thing with fiber is one end can have one connector, the other end could have a different connector. They can vary. So you can have an SC to SC or an ST to LC. If one side has one type of connector for fiber and the other end has a different connection for fiber, it works. Where with copper, you only have very specific types of heads, and that is it. Comparison, distance, if we're talking copper-based cables, lower distances. Copper is susceptible to EMI, RFI, other electrical issues, though copper cable is typically cheaper to install. Bandwidth is always an issue because newer copper-based cables show equal length when it comes to the actual speed of the cable. So got to keep that in mind. Right now, copper-based cables are tapping out about 10 gig. though newer category cables can actually reach the same 100 gig that fiber can. But fiber has the distance, meaning fiber is way further than our copper can. Moving on is our wireless networks, our wireless media. Again, our wireless will carry an electromagnetic signal representing binary through the airwaves, provides greater mobility. Limitations are going to be how far the wireless can go, coverage area. If there's anything interfering with that, that's interference. Protection in form of security, and shared media. Wireless LANs operate in a half duplex, meaning they can only send or receive at a time. Also, with wireless, the more users using it, the slower it becomes. Common types of wireless are the traditional wireless, IEEE 802.11. That's what you'd see in a home. Bluetooth is 802.215. Again, that's going to be Bluetooth like your phone and your car, things of that nature. WiMAX is going to be a lower speed but greater distance wireless using the old TV. We have Zigbee, which is some form of IoT communication standard, though Zigbee is not the only one. So we're talking standards for wireless. We're talking things like antenna design, how the wireless reception and encoding requirements are going to be, the frequency, the power of the frequency, how much power can we put on the wireless device. That also equates to speed and distance. Data radio signal methods are another big one. All of these are outlined in IEEE standards for wireless. So with 802.11 being traditional wireless, we need to dig into that a little deeper. Typical in a wireless, like a home wireless setting, we have a wireless device, your computer, your phone, your laptop, and that's going to have a wireless NIC. We have the device that will then control the wireless signal to put it on a wired network. That's typically some form of wireless access point, and that allows the wireless connections to be copied to or to be transmitted over a wired network. In a home setting, that may be a wireless router, because that's going to be a router and wireless access point built into one. If we're talking enterprise, we may have dedicated access points, sometimes called a WAP, wireless access point, or an AP access point, that allows for wireless to be distributed throughout a building, and then each of the access points would be hardwired back to the wired network. We actually have a packet tracer where you're doing this. And that is it for this chapter. If you have any questions or concerns, please reach out. So what did we learn just overall? We learned about different types of physical layers, STP, UTP, coax. We learned about some of the key standard protocols like IATIA, IEEE, IANA. We talked about the functionality of layer 1. We talked about multi-mode fiber. We talked about single mode, multi-mode, single mode being further, multi-mode being LED and quite can't go as far. We talked about wireless. We talked about IEEE 802.11, Wi-Fi. We talked about Bluetooth, WiMAX, and we talked about basically how a wireless LAN operates using an access point and wireless NICs. Lastly, we have another packet tracer about connecting devices and troubleshooting. And that is the end of this lecture. Again, thank you. And if you have any questions, please reach out. Thank you.